Good morning, everybody. Welcome back to class. My apologies for missing class on Monday. I hate missing class, so I hope you know that I really regret that I wasn't able to be here. Hopefully you were able to watch the lecture video. And so what we're going to do today is try to wrap up Chapter 6. Our next midterm is next Wednesday night. Of course, we don't have class on Friday for fall break. So we basically have 2 lectures left. We want to spend as much time reviewing as possible next Monday and Wednesday ahead of that midterm Wednesday night. So when we were looking at the Bohr model where we saw that hydrogen atom can transition from n equals 1 to 2 to 3 to 4, what we're really transitioning is, we were seeing towards the end of the notes, that the electron was just transitioning its radius to a larger orbit size as we're going from n equals 1 to 2 to 3, etc. And one way to think about what's going on at the sort of the spinning level of that electron, if we look at the like sort of 2 points on a like XY axis, that you can see as you go from n equals 1 to 2 to 3 that you're increasing the number of nodes, the number of times that the sort of electron passes that radius. Now if you imagine this point, the 2 endpoints wrapped around a circle, then that's the atom. That's the electron trying to spin around the nucleus of the atom. And so we really have, the electron trying to spin around the nucleus, and then it's hard to picture what it would look like to have a node through the nucleus. So it's kind of hard to picture what this is going to look like. This is we're picking up 1 node, 2 nodes, 3 nodes as we go from n equals 2 to 3 to 4. We're going to come back a little bit later and kind of see what that means in terms of where we expect to find the electron. So we're going to look at some radial probability functions a little bit later in the notes. But for now, the idea of quantum mechanics kind of kicks in, that as we go from n equals 1 to 2 to 3, that we're moving the electron further away from the nucleus on average, and then having these planes of 0 probability of finding the electron. So the nodes, this is a point where there's 0 probability of finding an electron. And so we'll see this again come up later, the idea of nodes. So we'll come back to what a node looks like in a. But the idea here is getting into sort of, instead of thinking the electron as a discrete particle, where it's at some location at some moment in time, let's start to think about where we kind of expect to find the electron in terms of more of a probability distribution. And that is really the notion of orbitals. And so the notion of orbitals is trying to represent where do we sort of most probably expect to find an electron. Well, for a 1s, or like an n equals 1 electron in hydrogen, the electron's most probably found pretty close to the nucleus, somewhere in that sphere spinning around the nucleus, sort of spinning in all 3 dimensions. And so we would have a probability relatively close to the nucleus and a lower probability further away from the nucleus. And you can imagine, and we'll see some of these plots a little bit later, that as you go from n equals 2 to 3 to 4, the shading is just getting a little further away from the nucleus. So as we increase an n value, our probability is just becoming higher, further away from the nucleus. Now, I should say that at this point in Chapter 6, we're going to start heading towards something you've probably seen before, that is electron configuration. So if you remember doing things for like carbon, 1s2, 2s2, 2p2, those sort of things, that's what we're going to be coming to, is sort of how do we know the sort of order that orbitals are filled into, and then how do we know what orbitals, like what are s orbitals and p orbitals and those sort of things. So one way that these orbitals come about is through quantum numbers. And so if we can understand the quantum numbers for an electron in an atom, we can sort of understand the general location of the electron in the atom. And so each orbital is described by sort of where its electron is, but it's described by 4 quantum numbers. And so an orbital by 3 of the quantum numbers, and then an electron can have an electron sort of spin up or spin down, so 2 electrons can occupy an orbital. So the 4th quantum number is describing that 2 electrons can have opposite spin within an orbital. So for something like a 1s orbital, so this is going to look like you have a nucleus, you can have electrons spinning one direction, then you can maybe put a second electron in spinning the opposite direction. So you can have 2 electrons, one going one way, maybe clockwise, the other one going counterclockwise. And so one way that sometimes we demonstrate this is just with sort of a line for a 1s orbital for spin up and spin down electron. Sort of showing that there can be 2 electrons within the orbital with 1 electron spinning one direction, the electron spinning the opposite direction. And so then the range of values, and like we'll have a couple of slides to try to introduce us to what these quantum numbers are really referring to, but just like a quick little introduction to the other three quantum numbers. We kind of were just talking about the magnetic spin quantum number. But the principal quantum number n, that's like the value from the H atom from the Bohr model, the n equals 1, 2, 3, etc., is referring to the n value of an orbital. And the n value is directly proportional to the size of the orbital. So as n goes up, the orbital increases in size. And so the n value takes on whole numbers from 1 to 2 to 3. And the key is that it can't be any sort of fraction or numbers in between these values here. So one of the other quantum numbers is the angular momentum quantum number. This tells us something about the shape of the orbital. So the L value can have the range of 0 all the way up to whatever n minus 1 is. And so this is where things get a little bit confusing, because we can start to imagine an n value, like let's say n equals 1. If n were to equal 1, the only possible value of L is equal to 0, because the maximum L can be is n minus 1. And so then, if we can imagine a different n value of n is 2, then L can be equal to still 0 or 1. So the range of L values goes up to n minus 1. Now, L is telling us something about shape. I don't want to get too far ahead of ourselves, but you might remember, you may have seen this before, that L equals 0 is telling you that that's like an S shape, a spherical shape. L of 1 is a P shape, kind of like a lobe or an infinity sign. L equals 2 is a D shape. L equals 3 is a F shape. Gentlemen, if I can hear you here, you're disturbing everybody. Thank you. And so then the magnetic quantum number tells us the projection of the number of orbitals that are possible with that L value. And this would range from minus L through 0 to plus L. So let's say we have a particular orbital where n is 3. Let's consider the possible L of 2. L could be 0 or 1, but let's just think about L being 2. Then a range of m sub L's goes from minus 2, minus 1, 0, plus 1, plus 2. From minus L to plus L. Now the projections are telling us how many orbitals there are possible with that sort of n and L value. So there's 1, 2, 3, 4, 5. So as I start to look here and see my n is 3, my L is 2, this is our D shape. We'll see what a D shape looks like if you haven't seen it in a couple of slides. But a 3D orbital is what this is referring to, and that there's 5 of them. So the 5 of them comes from this range here. So there's 5 3D orbitals. And so the projection is kind of telling us how many different ways there are to project that orbital into three-dimensional space. So if we take a step back, let's go simpler. Let's look back at n equals 1. L can only equal 0. So if we have n equals 1, the only possible value of L is 0. Then the only possible m sub L is 0, meaning there's one possible orbital with this set of quantum numbers. So we would have the 1s. So the 1 is referring to the n value, the s, the shape we get from the L value. And so then there's one of these orbitals that are possible. And as we start to think about quantum numbers, the periodic table is like hand in hand. Like as you start thinking of there being one 1s orbital, that's why we have 2 elements in the first row. We have hydrogen, a 1s1, helium, a 1s2. Because we know hydrogen has 1 electron, so hydrogen's configuration is a 1s1. Helium simply puts that second electron into that same orbital, so it has a configuration of 1s2. Now, if for some reason m sub L were different, then we would have had more elements in that first row of the periodic table. But you can kind of see that there's only one set of elements in that first row, hydrogen and helium. So we have one orbital that can take those up to 2 electrons for those 2 atoms. Then as we kind of proceed, if we look kind of at n equals 2, we can have L equals 0. Do you see how the shape, like that spherical shape, the S shape comes from the 0, so this would be a 2s orbital. And the range of m sub L's is still just that one orbital, so there's just one 2s orbital. It's going to take that spherical shape. But then if I have n equals 2 for that other L value it can have now, so the first time we can have an L of 1 is when n is 2. This is our 2p orbital, or 2p set of orbitals. Now the set of orbitals comes from the minus L to plus L, so that m sub L minus 1, 0, plus 1. So from minus L to plus L, including 0, we get 3 2p orbitals. Now, a lot of the math and working through the numbers is on another slide in a couple of minutes, but this just starts to get into then why the next elements are lithium and beryllium. There's 2 of them, because they're filling in the 2s subshell with 2 more electrons. That's all it has room for. And then after we fill the 2s subshell, the 2p subshell comes next, and there's 6 elements across that start filling up into the 2p subshell. So when we look from boron across to neon, the reason why we have a group of 6 elements is because we now have a set of orbitals that can fit 6 electrons. Because I have 3 2p orbitals, we can fit 6 electrons into these. So we get 6 electrons total into those orbitals within one particular atom. Why 2 electrons? Well, that's the magnetic spin quantum number. The m sub s quantum number is either plus or minus a half, either spin up or down. So a lot of times we'll write in an orbital, we can have spin up or spin down. Now, the plus a half, minus a half is complicated. Just know that the idea is one has one spin, the other has the opposite. It's not necessarily the up is the plus, the down is the minus. It's just one is one spin, the other is the other spin. So the key here is just 2 electrons per orbital from this quantum number. So the quantum number n is sort of, we call it the shell. So the n equals 1 shell has 1 orbital. The n equals 2 shell, bigger shell, has the 2s and the 2p subshells. So the n equals 2 shell contains 8 orbitals. The n equals 3 shell would contain the 3s, the 3p, the 3d. We'll see a summary of this, but it's 1 3s, 3 3ps, and then the 5 3ds. So that's 9 orbitals. And so you can get a sense of just some vocabulary. I've talked about a shell, is talking about the n value. A subshell is an n and l value. It's like the 3d or a 4p or a 2s. Those are subshells. And then an orbital within the subshell is then the range of those orbitals is told to us by the range of m sub l values. So again, like the 3d orbitals, the d being L of 2, the range being 5 of those orbitals, yes?
How are we getting 8 and 2? -1?
So let's come to a slide where we have a lot of this summarized. So let me get off the slide. It's sort of as if at this point in the slides, we just have a lot of vocabulary. If we could all simultaneously understand and use, it would be helpful. So let me go over one last thing that I haven't talked about. That's right here. That is the Pauli exclusion principle says each electron in an atom has to have a unique location. 2 electrons can't occupy the same space. So they have to have, each electron has to have its own set of 4 quantum numbers. And so as we start thinking of an n, l, m sub s, for each electron in an atom, they each have to have their own space, like their own address, if you will. So no 2 electrons can share the same space. So let me talk about each quantum number, and then we'll come back to a slide that'll go through kind of and show for sure why the n equals 2 shell has like 4 orbitals. So let's come back to that question in a couple minutes. So again, the principal quantum number n related to size takes on values of 1 and up. And these are the values that we were talking about in the Bohr model. So when we were looking at hydrogen going from n equals 1 to 2 to 3, this is the orbital increasing its size. So the principal quantum number n proportional to the size of the orbital. The L value, the angular momentum quantum number, is telling us the shape of the orbital. And so the range of L values is from 0 up to n minus 1. And then so an L of 0 has the S shape, L of 1 a P shape, L of 2 a D shape, L of 3 is an F shape. And we'll see, again, in a few slides what these look like. The S is spherical. I think that's the easiest one to picture because it's just kind of a shaded ball of our probability being really close to the nucleus. The magnetic quantum number, m sub L, ranges minus L to plus L again. And so if we happen to know the L value, let's say L is 3 for that F set of orbitals, then the range of m sub L's just goes minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. And so this is where we're getting that there's one s orbital that's possible for a given subshell. There's 3 p orbitals from the range of m sub l values. There's 5 d orbitals, 7 f orbitals, so forth. Theoretically, you could keep going and go into g and h orbitals, but for elements on the periodic table, f is the last subshell that we fill into. So you could go from like 4 being the next letter after f, so g, and 5 being h, but practically for elements on the periodic table, they're not going to use any of those orbitals. So 6 going to I, etc. And so then this slide here is talking about the shape of the orbitals. And so the first box in the first corner is our S shape. That's our spherical shape. And then, so this is just telling you from 1s to 2s to 3s, the probability of finding an electron in a 3s orbital is now further away from the nucleus than it would be in a 1s orbital. So it's telling you the probability of where you expect to find the electron, where is it with the shading. So where the shading is where you have a higher probability of finding an electron, 3s orbital, just bigger than the 1s orbital. The p-shaped orbitals over here, so these are our p orbitals. So our p orbitals have one set of lobes, if you will, for each of the orbitals. So we have the 3 p orbitals, we call them px, py, pz, because the orbital would be on the axis of the atom. And so what we have is a nodal plane. So this is a node here through the nucleus of the atom. So our nucleus is at the middle. So our positive charge would be here in the middle. And we'd have the greatest probability of finding the electron on the axis of the atoms. And so we'd have the probability sort of here, here, and here in our atom. If you start to think about like your 1s and your 2s and 3s orbitals, that what the p orbitals are trying to do is it's trying to use the space in between the s orbitals. So it's really trying to pack electrons into the gaps you'd have between the n equals 2 and 3 shells, or where those 2 p orbitals are trying to use some space. And then presumably, if you notice there's no 1p orbital, there's no 1p orbital for maybe 2 reasons. One is just mathematical from our rules, is that when an L is 1, that's what p means, then the n cannot be 1. So just based on the quantum number rules, if n is 1, the greatest L you can have is 0, so therefore you can't have a 1p shell. And presumably, the space between the 1s and 2s just isn't great enough for there to be electrons found between those orbitals. And so orbitals are really just trying to find space that's not used by other orbitals. And so then if you start to think about a relatively bigger atom where you have s and p orbitals, the d orbitals start to use the space in between the p orbitals. So the d orbitals here, so these are our d orbitals, they're trying to use the space between our p orbitals. Remember, our p orbitals are on the axes. So I just tried to draw in kind of 2 of the p orbitals on the axes. Notice how the d orbitals are trying to use the space in between those orbitals. So the d orbitals are just saying, hey, I sense some leftover space. Let's pack some electrons into that area. And so there's almost a way of thinking of like a relatively big atom. Like if I think of, I usually do like scandium because it's the first element that uses a d orbital. And so for scandium, you can sort of start to think about like there being a 1s orbital, a 2s orbital, and then it has the 2p sort of subshell orbitals, and then we have the 3s. So if you're following the periodic table, we're going 1s, 2s, 2p, 3s, and then 3p orbitals here. So if you start to think about the 3p orbitals, we get the 4s being the spherical orbital. And then you see kind of this spot here. Doesn't it look like between the p orbitals there's some space that can be used for electrons? Well, that's where one of the d orbitals fills into. So one of our d orbitals says, why don't we use this space here? And this is one of our 3d orbitals. So orbitals are clever. They're just trying to find space that's unused by other electrons, because that's the whole idea. Electrons are negatively charged. They repel each other, so they can't just sit right on top of each other. So they each have to find their own little place around the atom. And so the d orbitals, 4 of them look like clover leaves. One of them looks kind of peculiar, has like a donut ring around it. But again, this is just trying to use space that's not used by other atoms. And so these orbitals are defined by having 2 nodes. The p orbitals is having 1 node. So we have 1 node on the p orbital. We have 2 nodes on the d orbitals. And then the f orbitals, this picture actually isn't even in the book. So you really probably won't ever see these pictures again anywhere. But the f orbitals just have 3 lobes for the most part, or an extra ring. So you either have 2 rings in 1 lobe, or you have 6 sets of lobes, or like 3 sets of lobes for 6 total lobes. And so it's just kind of using the space then not used by the d orbitals. So this is what the L value is telling us something about the shape of the orbitals. So the shape of the orbitals from the L value, the number of these shapes we get is from the projection, it's from the m sub L range. So we count up the m sub L numbers is how we're getting 1 for the s, 3 for the p, 5 for d, and then there's 7 f orbitals. And then again, the magnetic spin, plus or minus a half, so we can have 2 electrons spinning opposite directions around the nucleus. And this is for every orbital, so every orbital can fit, even those f orbitals that look pretty big, pretty spread out, still can fit 2 electrons into those orbitals. So we get 2 electrons per orbital, regardless of the particular orbital. And so again, just restating the Pauli exclusion principle here, that each electron has to have its own set of these 4 quantum numbers. No electron can have the same energy or the same location. And this means that every electron must differ in at least one of those 4 quantum numbers. And so if we look and use carbon for an example, as we go along, we'll see some more examples of coming up with electron configurations, but I just want us to link the idea of quantum numbers to then getting a configuration. For carbon, we have 6 valence electrons. So just coming back to kind of chapter 2, I think it was, when we were counting subatomic particles. We have 6 protons, 6 electrons for a carbon atom. And so here we're looking at how those electrons are distributed around the atom. So we'd start with the 1s with 2 electrons, the 2s with 2 electrons, and the 2p with 2 electrons. And if I start thinking of like a way to diagram this out, I might be picturing this one of 2 ways. One might be kind of picturing it vertically in terms of energy, that as we go to a bigger orbital, we go to a higher energy. Just like Bohr, when we went from n equals 1 to 2 to 3, we're going up in energy. So the same thing would happen here. So we'd have our 1s orbital being the lowest energy, the 2s being the next, and the 2p being the next orbital. And we'd be fitting in 2, 4. And then we kind of have a question. This is Hund's rule that comes up on a slide in a few moments. We want to maximize the spin of the electrons. We want to spread them out into the different orbitals. If I put 2 electrons into one orbital, they're going to repel each other more than if I put them in 2 different orbitals. And so we just spread the electrons out. It's kind of like if you have 6 plus charge here, 1s electron, 2 of them here, 2 electrons in a 2s orbital. You have 1 electron in a p orbital here. If you're another p orbital, wouldn't you rather be here, sort of free from the other electron? And so that's what Hund's rule is doing, is it's trying to spread the electrons out, maximize their spin. And so the key is for each of these electrons, you can sort of start to picture what their quantum numbers might look like. Like for here, you'd have n equals 1, L equals 0, m sub L equals 0, and then one of them has a spin of plus 1/2, and the other has a minus 1/2. So you have the spin up, spin down. And the same thing here, other than you have the n equals 2, but L equals 0, m sub L 0, spin up and down, plus minus 1/2. And then these values here, you'd have n equals 2, but L equals 1. And then they'd have m sub L's of either 0, minus 1, or plus 1. We wouldn't be able to predict, like we don't know which one, if one of them is 0 or plus 1, or if it's plus 1 and minus 1, just that they are 2 of those 3 possible quantum numbers, and that they're either both plus 1/2 spins or minus 1/2 spins. That their spins are the same as each other, but just whatever the sign is, not exactly something we can tell. But we can sort of start to piece together some information about these quantum numbers to make sure that we can see that they're different from each other in this atom. Another way we can write the configuration is just to orient the orbitals on the same line, so we can more easily draw these configurations. So we have our 1s, our 2s, and our 2p, and we'd have 2 electrons, 4 electrons. And the key is that this would violate the Pauli exclusion principle. I can't pair the spins in the same orbital because they would have the same L and m sub L quantum numbers and m sub s quantum numbers. And so another thing we might try to do is to do this. We'll see that that violates Hund's rule, where we want to maximize the spin. So we want to put the electrons both spin up, but in different orbitals. Okay, so this slide here is just kind of summarizing what we had just said. I think the next slide goes into, yeah, this is what I was hoping the slide would be, where it kind of summarizes for the first few n values. So n of 1, the only possible value of L is 0. So we have our 1s subshell. Our range of subshells is just that one s orbital. And then so we have one orbital possible within that shell. So the n equals 1 shell is just the 1s subshell, just the 1s orbital, and just 2 electrons maximum. The n equals 2 has the 0 and the 1 L values, so L can be 0 or 1. We have the 2s and the 2p subshells. So our range of m sub L is 1, 0, minus 1 for the 2p subshell. So we get 3 2p orbitals, but then just one of the 2s orbitals. And so that's where we get 4. So this was your question I had went on that. On why there's 4 for the n equals 2 shell is just from the 3 plus 1, I mean the 3 2p orbitals plus the 1 2s orbital. When we go to n equals 3, we have remember the last L value can be is n minus 1. So whenever n is 3, the highest L can be is 2. We just start at 0. So 0, 1, 2 gives us the 3s, 3p, 3d subshells. The range of m sub L is minus L to plus L, so we then pick up that 5th d orbital, or the 5 total 3d orbitals. So we have the 1 3s, the 3 3p's, and then the 5 3d's. And so that gives us 9 total orbitals. If we start thinking of electrons per shell, it's just n times 2. So we get 2 electrons for the 1s, 8 electrons into the n equals 2 shell, 18 electrons into the n equals 3 shell, and then we'll stop at 4. But 4 goes from 0, 1 to 2 to 3. So we pick up that 4f subshell. So notice that the number 4 relates to the n value. So a 4s has an n4, L0, L1, L2, L3. And our range just then picks up 7 f orbitals. So 1 plus 3 plus 5 is 9, plus 7 is 16. So we have 16 total orbitals possible within the n equals 4 shell. 16 times 2, 32 electrons. So if you start to see things like 6, 10s, and 14s, right, from this being 6 electrons, this being 10 electrons, this being 14 electrons, you start to see the sort of main group elements over here, our p block, our d block transition metal row is 10 across, and our lanthanide actinide series is 14 across. You start to see kind of these subshells in action on the periodic table.
If you look at the fourth row, the last segment is krypton, it can only have 32 electrons.
No. So it would mean that that the n equals 4 shell, just because krypton's in the 4th row, doesn't necessarily mean it fills the entire n equals 4 shell. So when we see krypton, when we get to its configuration in a minute, we're going to see that it doesn't actually fill through the 4f subshell. So when we get to krypton, it's not going to fill. It's going to fill through the 4d subshell, but not the 4f. So it's not going to quite have the 14 electrons in the 4f yet. If you notice how the d subshell, like the first row, go to like scandium or titanium. The first time we get that D subshell is the 3D. So they're filling into a 3D subshell, but notice they're in the 4th row. Okay? So when we get through krypton, we actually haven't even filled the 4D subshell either. We would have only filled the 3D subshell, and then we would have filled through the 3P subshell and the 4P subshell. Let's come to that in a minute. Okay, so, yes?
On the previous slide.
Sure. Yeah, so how many electrons can occupy the n equals 3 shell? I think we had just said this before, but this is just, our 3s, our 3p, and our 3d subshells. So 2 electrons here, 6 electrons here, 10 electrons in the 3d. And so we had kind of already answered this, so I think we can conclude that that's 18 pretty easily. You guys have a chance to look at this question here. So for a 3p subshell, what's its range of m sub L values? So take a minute here, and if you're digesting something from the previous slides, if you have a question brewing, let me know. So take about a minute on this one. right, so I suspect probably we mostly agree. I would bet that it's minus 1, 0, and 1 for the range of m sub l's. And I wanted to mention that we use this L value here for the range of m sub L. So the m sub L range for that subshell is those three values. So meaning for the 3p subshell, we get 3 orbitals for that 3p subshell. Now, what I wanted to make sure that we don't get confusing, I can do pressure 1 minute, is that when n is 3, L could have been 2. And so if L were 2, then the range of m sub L's is minus 2, minus 1, 0. You may have been looking at this answer here and saying, why is that not the answer? Well, that would be the range of values for the 3D subshell. So that's the range of m sub L's for the 3D. So D is where L is 2. So when n is 3, L could be 2, but L is just not 2 for the 3p subshell. The specific value of L for the 3p subshell is only the 1. So the range that L can be is 0, 1, 2 when n is 3. But for the 3p subshell, we're specifically talking about the L being 1. And so for when the L is 1, the range is minus 1, 0, plus 1. Again, coming back to there being 3 orbitals within the 3p subshell. So let's try not to confuse ourselves into thinking, well, what if L were 2? If L were 2, this would be the 3D subshell. So for 3D, the answer would be B. So we said, what's the range of m sub L values for 3D orbital? The answer would be B. For the 3p subshell, D.
Will every P subshell, regardless of n,
Yep.
always have -1, 0, and 1?
Yeah, so like, yeah, every P subshell has that range of m sub L's. Every D subshell as well. And so then as we start to think about the probability of where we expect to find these electrons, this is where these probability distribution functions come into play. This is kind of almost where we get the shape. Like this is where we get that spherical shape as we have a symmetrical probability of finding the electron around the atom. This is where we kind of get this like contour plot, like 1s type orbital for hydrogen, for the 1s orbital. And if we said, well, what's the probability look like for the 2s orbital? Well, do you remember how the n equals 2 should have one node? And so here's that one node here. So there's a region of 0 probability. So if we actually look at a 2s orbital and we kind of like take a chunk out of the orbital, we'd see that there's some probability of finding the electron, then a point of 0 probability, and then we have our electron density here, and it would like fade off to that node. So we'd have sort of a probability of finding the electron close to the nucleus, but then greater a little bit further away. So our greatest probability far away from the nucleus, then we pass a node, a region of 0 probability of where we expect to have 0 probability of finding the electron for the 2s. So the 2s orbital has one node. So one like radial node, we often call this. So it's a node on the radius of the atom. And then the 3s orbital would have 2 radial nodes. And so if we, I think it's the next question, the number of nodes be for, oh, maybe it's after the slide. One of the questions is going to be, well, how many nodes would like a 5s orbital have? And it would be 4, because our n equals 1 has 0. So but we'll pick up with that question in a minute. This slide is showing us the orbital picture for a 2p subshell versus the 3d subshell. So notice the 2p subshell has 0 radial nodes. So the first time that you have an orbital like a 2p or a 3d, you don't yet have any of these radial nodes. So the first time we had that for the s, so 0 radial nodes here. We have no nodes along the radius of a 2p subshell. If you look carefully at the 3d, there's 0 radial nodes here as well. And then when you move to their next subshell, the 3p, it's hard to see here, but if you follow the 3p, it's this one here. So the 3p, it's the second orbital possible within p, so it has 1 radial node. If I'm being perfectly honest with you, I don't understand why we teach this. This sometimes appears on tests, more on the s orbitals than on the p orbitals. But I just wanted to show you what it looks like for the p orbitals, so that the 2p, 0 radial nodes, and we pick up having 1 for the 3p, 2 for the 4p. And if you look at the 3d, it would have 0. If you look at the 4d, it would have 1. I mean, I think this comes from that, like, that first picture where we had, you know, from here we had 0 nodes, and then across here you had 1 node. And so it's just as you go from the first to the second orbital possible, you're just increasing from 0 to 1 node, and then upward from there. And so this is about as tricky, and it's still a pretty simple question once you see the topic. I think it becomes kind of extraneous on what this really means in terms of any properties of an atom. But how many radial nodes does a 6s orbital contain? Well, this just comes from a 1s having 0, so the 2s having 1, 3s having 2, 4s having 3, of course, 5s 4, so 6s would have 5 of these nodes. I've never seen them ask this about a 6p orbital, but if for some reason it said, well, what about a 6p shell? How many nodes would this have? Well, this would just come to a 2p having 0, because it's the first one possible. Then the 3p having 1, 4p having 2, 5p having 3, 6p having 4 of those radial nodes. Again, not sure why we'd ever ask this or why it would be important to ask, but that's how we would figure out the number of radial nodes for a p orbital. Okay, so then as we go from quantum numbers back into the concept of coming up with electron configurations, hydrogen, this is what we were talking about earlier, having 1 electron. So it has that 1s1 configuration. We fill 1 electron into that most stable or lowest energy orbital, the 1s, the one that comes first. 2 electrons for helium, 1s2 for the ground state electron configurations. Lithium, the next element, so we have 3 electrons. So we go 1s2, 2s1. So 1s2, 2s1. And so the superscript, of course, refers to the number of electrons within that subshell. And so then let's see that Hund's rule in action. So Hund's rule says that when we're filling degenerate orbitals, this means equal in energy. So when filling equal energy orbitals, so orbitals that are of the same subshell, so degenerate orbitals are orbitals in the same subshell. So the same subshell would be they're all, say, in the 2p subshell or the 3d subshell, so therefore they all have equal energy. So Hund's rule is getting at when we're going from, say, boron, so boron 5 electrons, so 1s2, 2s2, 2p1. And we saw this for carbon already, where we use the 2 orbitals to come up with our 2p2 configuration. Nitrogen just continues along. So if we need to put 1 more electron into a p subshell, we have a 2p3. So 1, 2, 3 electrons using the 3 2p orbitals to maximize the spread of those electrons in the atom, maximize their spin. But then once we then go to, say, oxygen, oxygen's not on the chart here, but oxygen would be a 1s2, 2s2, 2p4, it's next after nitrogen. So we'd have a 1s, 2s, 2p set here. So once you fill 3 in, you've maximized the spin. There's nowhere else to put an electron but then paired up with one of these electrons here. Conventionally, we tend to write the electron spin up, but that doesn't, again, mean that their m sub s is +1/2. It just means that all their spins are in the same direction. And then we pair up one of them. And usually we just kind of fill from left to right by convention. So then neon caps off the 2p subshell. And this is sort of where, if you haven't seen it already, where you can begin to understand that the noble gases just fill that last 2p subshell, or the NP subshell, for a stable configuration. So the noble gases are just kind of capping off that subshell, coming up with a stable count of electrons in the process. So we sort of fill a subshell here, helium filled a subshell, etc. So then sodium just continues on, and you can almost look at the sodium, magnesium, potassium, calcium down the alkali-alkaline block. That's an S block. So those elements there are always putting their last electrons into an S subshell. And then the transition metals next over, we're going to see that they're putting their last electrons into a D subshell. Okay, so Pauli exclusion principle says that no electrons can have the same set of quantum numbers. So Pauli exclusion says we can't do this, that would be wrong. We don't want to put 2 electrons with the same spin. Hund's rule says we want to maximize the spin. Hund's rule would say you don't want to do this with spin up, spin down. You want to do both spin up or both spin down, but both paired in the same direction. And like I mentioned, more or less by convention, we tend to write them spin up usually. So whenever I'm filling in a diagram, usually I'm writing these spin up. Spin down is technically legal. There's nothing illegal or wrong about writing those electrons spin down. So this is okay, just maybe not typically how we do it. Okay, so then what are the orbital energies for the other orbitals? So we kind of seen you go 1s, 2s, 2p, 3s, 3p. If you notice through 3p, that's just kind of the order of n and then l. So you're just going from 1 to 2, s to p. So then we go to 3, and then s to p. And then the question is, do you go to the d subshell next, or do you go to the 4s next? And the best way to answer that question is to go to the 3p subshell. So filling through 3p is argon. Whoops. So let's look at the configuration of argon for a minute. So argon would be a 1s2, 2s2, 2p6, and then it fills into the 3s2, and then 3p6. So it fills that 3p subshell. And so then when we're going to the next element being potassium, you may wonder, well, does the 3d come next, or does the 4s come next? And the periodic table tells you it's the s, because potassium's in the s block. It's in that block of elements that share that s block. There are two elements across. And so the S comes next, then the D. So potassium would be we can condense this, say it's the configuration of argon, so you don't have to keep writing out 1s2, 2s2, 2p6, 3s2. So we can just say, well, this is argon, and then following that we go a 4s1, and not a 3d1. And then for calcium next door would be a 4s2. And then for scandium, argon 4s2, and then we go to the 3d. And if you're like thinking, well, how do I know it's 3d and not 4p? Well, there's 10 elements across next. And so the atomic numbers kind of tell you that the next elements are filling into a d subshell because there's 10 of them. Okay, so then we go 3d, and then we'll see that you go 4p, and then you come back to the 5s subshell. And so if you look at your periodic table this way here, now it's important to kind of recognize that we tend to take these elements here and pull them down here just as a matter of space. So in order to print this periodic table and not have it be like 30 feet long, we just move the F block down below. And we do this so you can put it nicely in like a book cover and all that. And so, but there's no reason why we don't make a periodic table that looks just like this one here. And you can kind of see, if you think of your periodic table here, you see you start with 1. The first time you get a P subshell is in that second row. And the first time you get the D subshell is actually in the 4th row, just by nature. So by determination of nature and how they spread their electrons out and use these orbitals, the D doesn't come up until after the 4s. So we fill across the D block, then we go to the 4p, then 5s. Then you may be wondering, do we go to the 4f next? Well, no, we just go straight across to the 4d. And you could sort of see that too, as you go from strontium at 38, yttrium's 39. Zirconium's 40, not cerium and praseodymium down in that 4f block. So we don't get to the 4f block until we cap off the 5p subshell, and then we get to the 6s, then we go to the 4f. So it's not until we get all the way down to the 6th row that we start using that 4f subshell. And then we don't use the 5d subshell until the n equals 6 row as well. And then we cap off our 6p, and then 7s, 5f, 6d, etc. And so if you think of your periodic table this way and just start counting 1 at the top, 2p first, 3d is the first one, and 4f's the first. And if you come back to why the first time you get the 3d is with the 3, it's because that's the first time you can have an L of 2. The first time you can have an F, which is 3, is n equals 4. So the first time you can have a 4f subshell, the first time you have an f subshell is n equals 4. And so if you remember that the 4f's the first f block, 3d is the first d block, 2p is the first p block, you can very easily come up with electron configurations just by using the periodic table as your guide. Okay, so there's a question earlier on krypton. Let's do krypton. So for krypton, we'd have, and let's start with argon, because we've gotten through argon. So we had argon, and then 4s2 was potassium and calcium. We filled 10 across the D block, so we do a 3d10. because the most we can get into that D subshell is 10. And then we should fill 6 into that 4p subshell. And so if you're counting electrons, krypton should have 36 because it's element number 36. We have 18 within argon. Then argon's configuration has 18 electrons. And then plus 2, plus 10, plus 6 gives us the 36. So the question earlier was krypton's in the 4th row. The fourth n equals 4 shell holds 32 electrons, but we're not yet using the 4f or the 4d subshell. So we're only using 8 of the possible electrons we can pack into the n equals 4 shell. So that gives us our 36 electrons. Let's maybe stop and look at selenium. Let's go back to, so selenium has 34 electrons. So it looks a lot like krypton, other than it's the argon 4s2, 3d10, 4p4. So we just lost 2 electrons out of the p subshell from krypton. And so the key is like thinking of our diagram for selenium, this is an E, is that we have the 4s, the 3d, and then the 4p. So we'd have 2 electrons in the 4s. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the D subshell, and then 1, 2, 3, 4. So sometimes we'll ask a question like, how many unpaired electrons does an atom have in its ground state electron configuration? Well, for selenium, it would have 2 unpaired electrons. 2 electrons that aren't paired up with their spins. And the reason why we might ask that question is you usually can't get that question right if you don't have the right configuration. Like we could say for like manganese, how many unpaired electrons does manganese have? Well, for manganese, we just back up a little bit further. Manganese only has 25 electrons. So we have the argon configuration followed by a 4s2 followed by a 3d5. So 18 here, 2 here, and then we're 5 across. You can also count scandium, titanium, vanadium, krypton, manganese, so that's 5 across. And so in terms of a configuration here, or a diagram, we'd have 2 4s electrons, and we'd have 5 unpaired electrons. So we'd have 5 electrons spin unpaired, electrons within manganese. Okay, so titanium, kind of got ahead of myself with some of the examples on the previous page, but titanium's just kind of like manganese. You know, so we're coming up with the argon configuration, 4s2, 3d. Now titanium is just 2 across, so 3d2. You can double check, titanium should have 22 electrons, it's element number 22. So we have 18 for argon, 2 here, so that's 22. How many unpaired electrons? I think you can probably agree that it's going to have 2. Now, another interesting question that we sometimes ask is how many valence electrons does the atom have? And the valence is kind of like the outermost shell. I think that's probably easy to understand that valence is the outermost shell. Or let's just call it the outermost electrons and not use the word shell. So what electrons do we count to be the outermost electrons? Well, we'd say the outermost shell for sure. So any in the highest shell of the atom, so the outermost or the highest shell. Let me actually write that as highest. I think it's slightly clearer. So the highest shell electrons plus any lower unfilled subshell. You know, so for the shell, that's the n value. So the highest shell for titanium is 4, it's the 4s. So we definitely have these as the outermost shell, or the highest shell. So we're going to add these 2 to our valence count. And then the 3d2 is an unfilled subshell. So this here, we call this an unfilled, lower than that highest and outermost shell. So this is a lower subshell. So it doesn't make us add all the n equals 3 shell electrons to the valence, but just those two. So we add these two. And so we'd have a valence count of 4. So just to conclude, we would take the outermost n value, whatever that is for the atom, and then we would add anything in an unfilled lower subshell that's not yet filled. Yes?
I think they were saying something about like anything with like the value like under 30.
Any under 30, so that's like zinc. I mean, I think once you fill like the 3D subshell, you're just not counting. Once you get to a 3D10, it just doesn't count towards the valence. And that would happen once you get to zinc. So, yeah.
How can we have a lower shell unfilled?
Well, it's like you notice how we have a 3D2, we could get up to 8 more in that shell. So until we get to a 3D10, that 3D shell is open and still being filled. And so if we're trying to count the outermost electrons, we're going to count for sure the 2 and the 4s, but then we're going to count the 2 and the 3D because it's not yet filled. So the highest n value plus whatever's in a lower subshell, a lower n value that we haven't yet filled. Let's go back to selenium for an example. So we saw selenium before was the 4s2, 3d10, 4p4. And so here we're not counting these 10 towards the valence because that d subshell is filled, and the highest n value, the highest shell is 4, so I get 6 valence electrons. So the 4s2, the 4p4, the highest shell. So notice we're counting the highest shell, not subshell. So the highest shell plus anything in a lower unfilled subshell. If you go back to manganese, manganese was a 4s2, 3d5. That would have 7 valence electrons. So valence electron counts in a way trivia question, but in a way just seeing if we understand how the configuration is interpreted in terms of that count.
So for zinc, which has the 4s2, 3d10, we have 10 or 12 valence.
Yeah, good question. So for zinc, what I would say, and I think the book would agree, is that once you fill that 3D subshell, it's full. So for zinc, we'd have a 4s2, 3d10 on top of argon. And so I would say just 2 valence electrons. And now this also makes sense because if you remember from zinc, from nomenclature, it only forms a +2 cation. If you look at a lot of the other transition metals, they lose like random numbers of electrons. Like, for example, manganese can form a +7 cation or a +2 or a +5 cation. But zinc only a +2. It's never really losing those D block because they're kind of stuck and locked into place. So these are not counted towards the valence because it's full. So once it's filled, those electrons wouldn't be counted. Okay. So then for, we could determine a configuration or determine an atom from a given configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 6 across into the D block. So one thing you can do is just count all these electrons up. If we count the electrons, we'd come up with 26 electrons. You can also look and see which element is 6 across the D block. That would be iron. So a few ways, you can just like look for the placement and take the last count, the 4s2, and then 6 across the D, or you can just count all the electrons up, get the count, look for the right Z for iron. Okay. So for a tin atom, let me skip this for now. That's just a summary. I wanted to come to one last thing before we take off today. I skipped over, and let me example. Inspect a chart like this one here and kind of see that when you look across the 3D and 4D subshell, sometimes the configuration isn't exactly the one you predict, but it's just where one electron moves from one subshell to another, but the total count remains the same. Okay, what I'm going to do, which is that some elements have a configuration we don't expect. So some things like chromium have a configuration that's unexpected. Like the configuration of chromium turns out not to be what we expected, which would be argon, 4s2, 3d4. But it turns out to be 4s1, 3d5. So some electrons have what we call an anomaly. They have a configuration that we didn't expect. In this case here, we could just say, well, the real configuration would look like this. It would have 1 and then maximizing the spin. So we end up with 6 total unpaired electrons. So that's how this is discovered, is you count the number of unpaired electrons in the real atom, you get 6. And so that would be consistent with this configuration, not this configuration, which would only have 4 unpaired electrons. And so we have 6 valence electrons and 6 valence electrons. Okay, now you don't have to know and predict which atoms have these anomalies, but some configurations aren't as you expect. Say this on a slide here. So I will make a video of the examples I missed, just to do a few more examples on configurations. So the slides I skipped, I'll make a separate video, upload that, so you have that material to look at before you do your final preparations, maybe over break. So that's it for this week. Fall break on Friday, no labs or recitations tomorrow. Have a great break, and I'll see you back here on Monday.
I'm glad you're feeling well again.